Good afternoon and welcome to PCT's session on using non-destructive testing equipment and ground penetrating radar to take measurements of new structures. In particular, what I'm talking about today is some of the system in our range where they can directly measure a parameter of a structure. That might be thickness of a concrete slab. It might be locating the position of embedded objects, or it may be something where we're looking at the depth of a pile. So I'll be discussing, in the order I've got here, I'm going to start with ultrasonic dry film thickness gauges. These are very commonly used to measure paint thicknesses and waterproofing membrane thicknesses. And I've been taking a particular focus with making sure people understand these tools, how to set them up, how to use them to inform decisions around the final cured thickness of waterproofing membranes. We'll then go to what probably the most commonly used non-destructive tool for measurement, which is cover meter measurement. Cover meters specifically measure the depth of reinforcing steel from the top of the concrete surface to the top of the reinforcing bar. They're a very important tool in ensuring sufficient cover is achieved, which plays into aspects of concrete durability, the design life of structures, and also just confirming the reinforcing steel is in the slab and where it should be. Ground penetrating radar can be used to take measurements, particularly the location of embedded objects. So that goes beyond reinforcing to other embedded objects and more complex forms of structural reinforcing like post-tensioning tendons. So I'll discuss a little bit about how depth needs to be considered and positioning needs to be considered when doing that sort of measurement. Then I'll jump quickly to impact echo, commonly used for the thickness of concrete structures and foundations. And continuing with foundations, I'll finish up talking a bit about sonic echo measurement, or pile integrity testing, you may know it as, or low strain testing of piles. So, this is going to be my first topic. It'll be looking at ultrasonic dry film thickness gauges, and I'll sort of start with the same discussion for each system, where we'll look a bit about what it can measure, the quality of those measurements. Some things will only measure one thing, others will have quite a broad capability. We'll look at the particular things that a user needs to consider before he starts to take measurements. Is there calibration, documentation he needs to keep up to date? Is there adjustment or a parameter he needs to enter? Because when we say measurement, we don't necessarily mean a direct measurement like you take with a ruler or a caliper. It's very common that we're using some other element of physics. We may be sending sound into something like the ultrasound into the coatings here. We may be using radars or doing something other a little bit more abstract and recording a value that is not immediately millimeters or some other parameter. It may be something like speed of time of transmission, or we may get a more complex output. So with the ultrasonic gauges here, we'll see that we actually get a graphical display of the sound coming back to our gauge, which we then, as an operator, need to interpret, because the machine's going to give us a number, and that number is useful, but we need to make sure that number is taken from the right part of the returning signal. So, and that's probably the biggest difference between using a non-destructive tool to take a measurement than taking a destructive measurement or measuring with a ruler or other mechanical device. Is we need to make sure the gauge is operating correctly, is correctly calibrated, and any input it needs, such as speeds of sound, reinforcing sizes for cover meters and other information, are correct before we trust the numbers it gives us. And there needs to be some verification along the way, whether to samples we've prepared ahead of time with known measurements or to information we have prior to construction. So for our ultrasonic dry film thickness gauge, we need to know we've chosen the right device for the kind of coating we want to measure, which might be paint on concrete or board walls. It may be the thicker waterproofing membranes or specialist membranes such as a polyurea or cement modified membranes, which can be a more difficult measurement than just a pure paint. Now, these DFT gauges are supplied with a calibration certificate, and if we're going to use the output from them in microns, we do need to confirm that that output is verified on a reference, either a generic sample or preferably working with samples of the particular membrane material we're actually measuring. It's also really important that the operators review the output of the machine, the graphical display of sound return, to make sure the number that the gauge has given has been chosen from the correct part of the returning signal, and also that the returning signal is consistent with the correct measurement. I'm not, now, that's a bit, the exact procedures beyond the scope of what I'm discussing today, but I just wanted to, but I will be using this to show some examples and just highlight the correct mode of thinking. If you did need more detail and you were a user of these gauges, I've got a standing offer. I will train anyone to use a Defelsco Positector gauge, the 200 range, to correctly set it up and use it for your application. So do get back in touch when I send out the wrap-up email from this presentation, or give me a call, and I'd be very happy to go in a little more detail. I've just got a note that I may not be coming through clearly. Is that anyone else noticing that? Or is that a network issue?
I think it's a network issue.
Okay, thank you very much. I just wanted to double check that.
No worries, mate.
Okay, so, and just to give you an idea of what I consider the risks of using ultrasonic gauges, I think the biggest risk is trusting a simple machine to do the thinking for you. If you have a look at my picture of the gauge in the top right, where it's just giving us a number, your gauge should never look like that, because then we don't know where it's taken that measurement from. So you need to review and confirm the choices any automated process makes. Now, specific to using an ultrasonic gauge, you do need to be aware of the surface finish and using sufficient contact gel to get the sound into the surface, into the coating material. You need to make sure it's adjusted correctly, that you haven't set the device to not read measurements over the range you care about, or that you've done something else which is having it make the wrong choice. And the other thing, which is rather important, is you don't want to take a single value. It's not valid to take several meters squared of waterproofing, measure one spot, confirm the measurement's good and a valid measurement of thickness, and use that one spot to indicate the conformity of the entire area. You do need an approach where you are averaging several measurements in a small area to confirm that they're all consistent and representative, and also that you've checked different areas of your test subject, so to see that you understand the whole story, because a single spot is just that spot. So just a little bit more on the theory. The ultrasonic measurements, there are American and international standards that define the test. To the Defelsco Positector range, they do offer graphical video. I recommend this to everyone doing waterproofing measurements. I do think just because that's a more complex setup than measuring paint, you simply have to be able to review what the machine is doing. I know I'm saying this a lot, but I really do believe in the operator seeing what the gauge has done and confirming. The physical principle is when we change from one distinct material to another, we get a returning echo, a sound wave return from the ultrasonic pulse from the gauge. In this example, it's gone through two layers. There are two clear reflection peaks on the chart, and the gauge, using its automatic pick, has picked the tallest peak and recorded a thickness of 75 microns. And if I was teaching operation, I'd go into a little more detail on how these automated choices are made and how to correctly and how to adjust if the machine is reading to the wrong reflection. Now, I say reading to the wrong reflection. How do you tell? Well, you've got to know what you're expecting to find and be able to match that back to what you are finding in the real structure. Now, there's several stages to make sure you're comfortable. Firstly, there is calibration provided with Positector equipment, so it's important to make sure that you've actually got that traceable documentation, make sure your gauge is operating correctly. It's also important to make sure, for the purpose of using it today, that you've checked its operation. So the 200 series is provided with a reference chip of a known thickness. It can be used to check that the gauge is still measuring that chip correctly. If the measurement is out, it's a little thicker or a little thinner than expected, you can adjust that gauge's readings to correctly match your verification sample. Now, practically, you may not be provided with a sample that, with a reference chip that perfectly represents your materials. The supplied one from Defelsco is a white plastic material, a reasonable model for paints and standard waterproofing membranes, but entirely inappropriate for materials like polyurea. So you may need to make these adjustments to your particular coating. And even if it's just a rough check, it's nice to compare samples of that material you've prepared off the final substrate, as an example, or samples you've cut from that substrate to make sure that it's adjusted and measuring correctly. Then finally, you need to think about how you're measuring to actually capture the real performance on site. So again, I'm not at all a fan of taking an individual measurement and calling it done. There's too much variation, even within a small area, maybe 10 millimeters diameter sample area. There will be highs and lows. There will be thicker sections of material. So you do need to collect and average your results, have an agreement if you're working for someone, how compliance will be measured, whether it's average or minimum measurements must be above a certain point. And you must have an approach from where you'll take those measurements, and whether there's a random sampling or other setup required to do that. So that's a brief discussion about measuring coating thicknesses with ultrasound. Does anyone have any questions before I go on to talking about cover meters? Okay, no problem. Thank you very much. I will keep going on the topics. So moving on to cover meter systems, we're still measuring thicknesses, but we're now measuring the thickness of the rebar cover, the thickness of the concrete from the surface to the top of the reinforcing steel. Cover meters, sorry, I'm going to mute that 1 second. Thank you very much. So cover meters are electromagnetic devices, and because reinforcing is not a flat plate, it's individual reinforcing steel bars throughout the concrete, we can also use a cover meter to locate the position of the top reinforcing steel, its location. So now, finally, electromagnetic eddy current cover meters do offer a bar diameter estimate, and that is an estimate, but that can be included in the list of possible measurements we can make some use of. The biggest factor affecting accuracy of a cover meter tool is that the correct bar diameter that is in the concrete structure has been entered into the cover meter, and that the correct positions for measurement have been chosen. Now, what do I mean by correct? Well, it's covered under the risks. We don't want any other metal, including reinforcing bars crossing at 90 degrees, to be within the measurement of the cover meter probe. And I'll show a measurement procedure as we talk that'll try and eliminate that influence. We also need to be aware that if there is other metal nearby, something as simple as a steel cap boot, tie wire, or embedded cabling, it may not be detected by the cover meter, but it will affect the measured cover depth. So the choice of the right places to measure is very important to getting the best values from a cover meter. Also, if the reinforcing steel is too closely situated together, bar spacing, somewhat less than 150 millimeters bar to bar, will begin to provide additional metallics, additional signal strength back to that cover meter, and there needs to be a correction with ProSec cover meters to account for that. Now, I do have saved on YouTube a previous webinar that goes into a lot more detail about cover meter measurements, but the key considerations for using a cover meter is setting up bar diameters correctly. That's where we get our depth conversion from, and making sure you're measuring in the right spaces. Cover meters are typically a pulse induction eddy current measurement. They see signal strength, so they produce an electromagnetic field about the probe. they record the returning matching signal from the reinforcing steel. So electromagnetic field is produced. It induces a current, electrical current in the reinforcing steel. This produces its own electromagnetic field, and we measure the strength of that electromagnetic field. That is the raw measurement from a cover meter. Again, it's not like a ruler or a caliper. We're measuring one value. So in order to convert from the signal strength to a depth, we need to enter reinforcing diameter. Now, we've got a defined range of performance for cover meters. So out to roughly 80 millimeters, you'll be within 1 millimeter of the real cover depth, which is very precise, provided you've entered the correct reinforcing diameter. Then it'll, at its worst, at the maximum range of around 140 millimeters, or a little bit deeper for very large reinforcing steel, you'll be at 3 or 4 millimeters precision. So this is information you can directly use. And that's why I call the cover meter measurement excellent. We've got defined performance and a defined procedure to achieve good measurements. So the rebar diameter estimate is quite a different signal. We're measuring with a weaker and stronger signal strength coming from the probe. And we're essentially looking up what the expected performance for particular reinforcing sizes would be. This measurement works down to around 40 or 50 millimeters depth. It's an estimate. I would not like to give a particular range of plus or minus on this measurement. It is an estimate. I have a comment from Harold about the aggregate and the concrete can have an effect on values. Now, that's true. For a ferromagnetic cover meter, for eddy current cover meters, they would actually need to be metallic and conductive to affect the measurement. But ferromagnetic cover meters certainly will have a performance effect from the aggregate. When I talk in a little more detail about the sources of interference, conductive metals are the big killer. Now, just talking about procedures, the most important aspect of getting the real reinforcing cover is you need to locate your measurement directly over a single reinforcing bar. And if you just go straight to a concrete surface, place your cover meter on that surface, you're not going to be correctly measuring that. So what we're going to want to do is actually follow a procedure to physically place that to determine the reinforcing, lay out the grid of the reinforcing. So to begin, I'm going to want to take a scan. I beg your pardon. So to begin, I'm going to want to locate the reinforcing steel in one direction. So I'll cross it usually 3 times to ensure it's straight, and I'll pick up its position. I am not yet recording the depth of the reinforcing steel during this stage of the process. I can now locate the reinforcing crossing in the other direction. And because I can situate my cover meter probe in between, in this case, the horizontal bars, I can correctly measure the depth to the reinforcing bars, provided I've entered a correct reinforcing diameter. And I'll take several measurements so I can get a minimum, maximum, and an average. You never want to take a single measurement with non-destructive tools. And finally, I can go back and record the cover depth of the horizontal bars. So again, I'll be discussing ground penetrating radar in a second. I'll run back and I will just present that slide in full screen. Thanks, Michael. So just to cover that again, we are physically locating our horizontal bars. Then we're locating our vertical bars and recording cover depth during that process. And then finally, I'm going back through and I'm recording cover depth of my horizontal bars now that I can locate the probe correctly distanced from the other reinforcing steel. So next I'll go into measurement of the ground penetrating radar. Does anyone have any questions on cover meters before I continue? Or comments? Again, it's as much a discussion as a presentation today, so please do let me know. We had a question about, is the profimeter any more accurate than the profoscope? So the profimeter and the profoscope are Prosec brand cover meters. They both use the same measurement procedure, an pulsed eddy current measurement, which operates to the same precision. If you have a look at my previous slide where I was showing precisions of cover meters, I actually had a chart talking about the profoscope and the profimeter cover meter. If I was choosing between these two options for my business, it would be more about, do I have to do complex work for which the profimeter has more adjustments and better visualization to make complex work possible? Something like measuring reinforcing cages and precast elements, I like a profimeter for. It's easier to deal with congestion and more involved reinforcing layouts. Whereas if it's a simple wall or floor every time, a profoscope's not going to struggle. But it is possible where you would achieve the same performance with either device, provided you take enough care with each device and choose good measurement spots. John asked if it is possible to know what to do if we do not know reinforcement diameters, which is a good question. With the discussion of as-built structures, often you will be able to get that information. If you don't know, it is possible to look at the range of possibilities. So this is another chart from the profoscope manual, which explains the variation in cover depth precision. Sorry, the variation in the measurements for if we have reinforcing bars that are bigger or smaller than a 16 mil bar, and we set the machine to 16 mil. So let's say you have a slab on ground, and there's a possibility that you could have bars from 8 millimeters to 16 millimeters. You could use this information to determine the additional uncertainty of your depth measurements and maybe make a conservative choice there when you don't know that reinforcing diameter. So there's definitely needs to be covered in your procedures if you can't get that information. I do hope if it for as-built structures, you would have the opportunity to ask about what's intended to be in there. But if you don't, there's ways to consider that. Do I have any more questions on cover meters before we continue? So Mal asks, what equipment is more accurate to measure the reinforcing diameters, cover meters or other? Well, I would say other because I'd use a drill. The cover meters will estimate reinforcing diameter. They're not good enough that I would really consider that measurement to be your master reference for diameter. And particularly when we are concerned about measuring diameter, it needs to be backed up by inspection. Again, for a new structure where we know what's in there, this becomes less of a question. But when we don't know, we've got to back it up with that physical confirmation. Again, if you want to talk a bit more on this deal, as I go into this question almost every time I discuss cover meters in other webinars, there is a little more detail on my previous cover meter webinar on our YouTube channel. I've got another question, which is, hi, if there's a tile on the floor, how will this affect the rebar diameter measurement results? It shouldn't affect the performance of the diameter because it's not a source of interference. It's merely a thickening apparent. If there was additional metal as part of installing that tile, it would affect the measurement. Also, if that thickening placed the overall cover depth below around the 40, 50 mil range for which the diameter measurement result will work, it would prevent the measurement occurring. Again, diameter is difficult. My preferred tool for diameter is physical inspection of the bars. And then maybe I could use a cover meter to confirm that other areas are similar. But I don't like it as a master reference for diameter. It's not the right tool for that. It is an excellent tool for the depth of cover. And that's the main purpose. Let's double check I've answered all questions on cover meters. Thank you very much. If I can, I will go on to talking about ground penetrating radar. So ground penetrating radar tools are our first scanning tool, which means we're no longer taking a signal strength or an individual signal measurement. So with our dry film thickness gauge, it was ultrasound, and we sent a single sound pulse and measured the signal that returned. With our cover meter, we just measure signal strength. With ground penetrating radar, we are now sending repeated pulses of microwave energy and recording the response. Particularly with the ProSeq instruments, we're using a slightly different principle. It's a step frequency continuous wave antenna, but practically we no longer get an individual measurement or an individual result. We get a scan, a visual representation of the structure. Within that visual representation, a skilled operator can interpret it to determine the position and depth of reinforcing steel, the position and depth of embedded objects, and if the concrete structure is sufficiently thin, we can also usually see the thickness within the range of the ground penetrating radar. Everything except the lateral position of objects will not be correctly recorded without some setup. Lateral position is based upon the physical wheels attached to your radar. They're encoder wheels, and they know how far it's moved left and right. So that's why object position is a measurement. We're seeing the position on the image produced by the scanner. If we line up directly on top of it, or we measure between two positions, we can determine that geometry as a direct measurement. But our depth measurements are indirect. Radars record time of transit for the radar signal in nanoseconds. We care about depth. So I'll talk about how we have to evaluate an appropriate value of dielectric constant to have a meaningful depth. You'll also notice that I've given our rebar cover depth here as good rather than excellent. Our cover meters were maybe 1 millimeter precision with the best performance and the best settings. With the operator having to determine visually the position of targets and the setting of a dielectric constant from outside, we're going to be close to the real thickness, but it's not going to be quite as precise a measurement as a cover meter will offer. So you've got two stages. We physically pick the target, and we also set a dielectric constant, so we understand our conversion from speed of radar to thickness. It's also important when you are setting up to scan where you can clearly see the targets, which is about space. And if you are doing lateral positioning, to have a fixed reference to begin. I'll have examples that look at that in both cases. Now, our big risks with radar is the quality of the output is down to the operator's skill. They are directly interpreting a visual representation of the internal structure. It's not a photograph. It's not a direct measurement. So the operator needs to pick what he believes to be his targets and record their positions and depth. If we have large amounts of reinforcing steel closely spaced, it can prevent information about what's happening underneath that. And particularly when we are using some of the 3D presentation tools of radar, the alignment of the reference points is critical. And I'll show what I mean in a second. So just a quick word on the physics. The ground penetrating radar, we send electromagnetic pulses, a signal into the structure. As we become close to a target, which we're crossing at 90 degrees, we will produce a hyperbolic signal, a little bit like a fish finder. What do I mean by that? Let me show that graphically. So the thickness of the concrete structure or a layer inside soil, if we're going over a flat target, the closest point for the radar is always underneath the machine. So we get a flat presentation for flat targets we're crossing parallel to. When we cross an embedded object perpendicular, excuse me a second, I'll just mute that sound. So when we're crossing an embedded object at 90 degrees, we start to get signal from that object before we reach it. When we are directly over top at the closest point of that embedded object, we have the peak of the hyperbolic signal, and then we still get signal as we pass beyond that embedded object. In this case, I've chosen a steel object because I also want to highlight the effect of steel higher in a structure, where it will shadow what's underneath it, so it can hide additional reinforcing or other targets if they're not clearly visible due to the hyperbolic reflections from them. So, first risk I talked about was alignment of the grid scan. Whenever we're showing one of these really quite clever presentations where we have the results projected over a surface, or we have a 2D slice or a 3D presentation of data, what we've done is we have taken several scans on an aligning grid. And when we take those scans, we're then able to stitch them together to get our slice or 3D presentation. So we can see here, this was taken on a waffle pod slab, so polystyrene void formers forming thickened ribs on the underside of the structure, which you can see here, and also with conventional reinforcing. And we can see where that conventional reinforcing laps. And everything's pretty well aligned on this. This was the hero scan. This was the good one. But what I want to actually show you is what happens when the scan isn't lined up correctly. This is a previous scan of the same area where it wasn't quite right. You can see these little sort of stitches and these little disconnects. And what's happened here is that when my colleague Stu was taking this measurement, he didn't align the radar correctly on some of his scans. What we would have done is, when he was placing the radar probe onto his grid, his alignment would have been, rather than straight on top of the 0 point, it might have been slightly after or slightly before the start line, with the visual effect that the reinforcing is no longer continuous. So if you are going to make use of 3D functions or scans where you're combining several measurements, this was taken with the GP8100 radar, so that's a array antenna, 6 scans per movement, so it's quite a large scan, around 3 by 4 meters. That initial alignment is the critical thing to get right to have everything to be in the correct position. Now, let's talk about depth. Once again, we're not directly measuring depth. We don't have a ruler. We're measuring time, the time for the radar signal to go down and come back. In order to know the velocity of that signal and mathematically convert to thickness, we need to know a property known as the dielectric constant. It's a unitless measure of material's ability to hold and pass a charge. Values from 1 to around 81 typically. The reason I highlight that is water at 81 is quite a large value. So it means that the amount of water in the concrete will affect the precision of depth measurements. So we need to adjust dielectric on the day we take measurements, not adjusting depth, but 2 weeks ago and coming back to the same site and considering that value to be okay. It's a measurement that you adjust each time you go to site. A couple of ways we can make the choices, and the quality of the input gives us the quality of the thickness measurements, along with the quality of the positioning pick by the operator. So specifically here, we could take a guess. 5 to 11 is a reasonable range for cured concrete. If we know the physical thickness of that constructed element, or if we know a precise depth, maybe from a cover meter measurement, we could use that to choose a dielectric to get those depths right and bring everything else into correct depth. Or it's possible to overlay the hyperbola on the scan with a mask that represents the mathematical shape of hyperbolas for a particular depth. So if you haven't taken one of these steps, the thickness value on the left-hand side of the scans is not meaningful. You haven't set it up. You haven't made the adjustment on that procedure of calibration, verification, adjustment, and measurement. So you've got to make that adjustment before you can go forward. Now, a few more risks. Now we are talking about as-built structures, which means the concrete may be quite fresh. This is going to have a big effect on the amount of water, so the dielectrics may be quite high. We may also have signal loss, so we may not go as deep as the physical devices normally can. A device that might achieve a 700 millimeters maximum depth may only achieve 300 or 400 millimeters or less in very fresh concrete. So we can lose signal. We need to take particular care with our dielectric adjustments. We also need to be aware of our biggest source of metal is that the surface is that reinforcing, is that metal can either interrupt the signal completely. If you're scanning on top of a metal plate, the radar's not even making it through the metal. If it's a steel fiber reinforced structure, that's just the same. It's not going to go in. And you can get the shadowing effects where metal above a target can cause shadowing underneath. In this example, there were shadows on the thickness measurement because of the metallic targets above it. Now, I did see a quick question. The question was, how do concrete overlays such as asphalt affect GPR scanning? Can you allow for non-uniform dielectric constants when GPR scanning to account for asphalt over concrete? That's a very good question, and you're quite right. It's not going to be a uniform dielectric. The asphalt is going to have a very different dielectric value than the concrete. So especially if that asphalt varied in thickness, it becomes very hard to get a really precise thickness calibration using only a single dielectric value. Now, the GS8000, which is the utility location radar from ProSec, actually offers multi-layer dielectric constants. You can set a gate. The dielectric above would be the dielectric calibrated for asphalt. The dielectric below would be the dielectric chosen for concrete. But that's not a tool available on other systems. And how it's quite white as well. There are other ways with post-processing software to take more care with it on something like a typical concrete scanner output. Now, I'll wait a moment because I'm sure there's a few more GPR questions before I go on. So bear with me. And if there's anything you'd like to ask, unmute or leave the notes in the chat. I'd be happy to cover those. And let other people provide their input before we go on. So I'll wait a moment before continuing. So how to measure size of rebar and voids using GPR? Very good question. First point, slightly controversial perhaps. I don't believe that on a normal ground penetrating radar scan, you have meaningful information about the size of reinforcing steel with a ground penetrating radar. The hyperbola shape is controlled entirely by the dielectric constant. You don't get a thicker or thinner one, or wider or shorter, or any kind of variation with a radar. It's just its position and its depth. Now, voiding is actually hard to see with radar in the first place. You could see on the scan of the void former material, the polystyrene void formers in that waffle slab, we could see the extent of that. And yes, we can get the size of a 1 meter by 1.5 meter piece of polystyrene, but we're probably not even going to see small voids honeycombing on a ground penetrating radar scan. It's almost a source of interference to radar scanning. Again, some of our previous presentations on radar go into a bit more detail about detecting voids with radar, but it is not the correct tool for void detection for quality control. If you're looking for honeycomb voiding or voids that aren't meant to be there and aren't a physical void former, so it's just better to work with something like an ultrasonic scanner, like an ultrasonic pulse echo scanner, to look for voiding. Continuing down the run, we have a question: can we accurately scan top and bottom Rio, both, or only top Rio? If your reinforcing reflections are visible for the top and bottom reinforcing steel, and your dielectric is correctly set, the depth information is meaningful for both top and bottom. The position information is meaningful. Again, diameter. I could, again, slightly controversial belief. I don't believe there's any information. I believe a few of the comments down I'll get to when we get there. Maximum thickness of concrete can GPR handle. Now, the depth of penetration of radar is controlled by the frequencies available to the radar. So on Pro6 range, their GP 8000 and GP 8100 radars have a maximum of between 5 to 800 millimeters, absolute maximum depth, see the bottom of the slab, because of their lower frequency content from the antennas. On their 8800, your maximum range would be around 500 mil. So if you sort of expect a performance no better than half a meter, it's a reasonable assumption with ProSig instruments. Other manufacturers can be a little different there. I believe we have really quite very good depth performance, but it's also possible to do things like use lower frequency utility location radar, which can scan to a greater depth, but may not be able to locate individual targets like reinforcing steel as effectively. Is it capable to scan minor cracks in concrete? I don't believe a ground penetrating radar is going to tell you anything about cracking in concrete. I just don't think there's any information. Commentary from Harold. A, D/E must be correct. B, must be sure the bars are tied. C, take several samples. I believe Harry's referring to trying to find the top of crossing reinforcing bars. Is that correct, Harry? We also have, yeah, so essentially if you have tied reinforcing, Harry's suggestion was to look for the position of the top of bars in physical contact, but I don't, again, not personally, again, I don't suggest that unless you've been working with radar for a long time. Certainly don't try to look at hyperbola shapes and take anything about diameter from hyperbola shapes. We've got a question about how long should you wait to scan freshly poured? You should, as soon as it's solid enough, you can physically use the scanner on the structure. It's not stopping you from scanning because it's uncured, provided it's not going to provided it's not going to stick to the scanner as it rolls over. You just need to understand that the performance will be degraded. You won't be able to see as deep, and you'll need to take more care with your dielectric settings. Oh, great. So James is sending on something about concrete layers, and that's actually a good point about delamination cracking. You can get some physical thicknesses, so debonding on that. So that's again another case where it is appropriate. Estimate of thickness of slab on ground. You can get the thickness quite well for slab on ground if you get the reflection. So if your soil is too similar in dielectric to the concrete above, you won't physically see a layer for that thickness. If you can see the thickness layer, you can measure to it. Will it actually pick up electrical conduits and or PVC drain within slabs? So if your conduits appear on the scan, so they're not hidden by steel above them, and you can see the hyperbolic reflection, you can pick it up. It is absolutely possible to find conduits and embedded objects that are not metallic with radar. But if you have very congested reinforcing, it may hide the signal from them. Certainly, one of the jobs people do with radar all the time is locate embedded conduits and services. Though if that is the main criteria you have for scanning, radar may not be the only tool you want to use. It's very appropriate to also use things like electromagnetic location ones to confirm the regions where those conduits and other targets are within the slab, and then use radar to match and find more precisely positioning where visible. Also, with all these scans, you wouldn't want to scan once. You'd want to take several scans, locate targets several times, and work out their path. Anything more on radar before I go on? Can we find the pier location under the waffle slab, or is it limited by depth? That can be limited by depth. So if your waffle slab thickness is below that maximum 800 mils, absolute maximum, or the performance in the day, it can be very hard to see what's happening beneath that. You could use a lower frequency radar. Essentially, if you have a pier and it's in contact with the thickened sections, you would essentially see the thickness vanish from your scan. So if you're successfully able to record the thickness of the thickened section of a waffle slab, and there's a region where it's vanished, that vanishing is commonly caused by the presence of the pier underneath, the radar going through the thickened section down to the pier further, not returning a signal back to the scanner. It is a job people do. usually with commonly with a lower frequency radar. It's a difficult job. It's not something you would do without taking several tools and working carefully. Can they pick up conventional reinforcing in a fiber reinforced slab? Plastic fiber? Plastic fiber, yes. Metal fiber, no. Glass fiber reinforced polymer. GFRP reinforcing, weaker signal, detectable, just like any other embedded object. If it's sufficiently different electrical properties, you can see the hyperbolic reflections from it. It will be a weaker signal than a metallic target. Okay. So let's go on from radar, talk a little bit about impact echo testing. So I'll talk here about theory, a little bit of practice, but let's again begin with our consideration of what measurement can we take. So impact echo is a technique that is used for two main purposes: to determine the thickness of a flat plate of concrete. So by a plate, we might mean a wall, we might mean a floor. We don't mean a circular column. We don't mean something with a complex geometry. And it's also used to determine if we've got voiding inside structures, but I'm not covering that today because I'm talking about measurements and thicknesses. Now, we do have to consider the speed of sound in the concrete, because that's used directly in the conversion from frequency to thickness. And I'll show how impact echo scans work, and I'll explain that. We do need to pick a good place. We want a plate of concrete, so a wall or a floor, in from the edges. I've got a presentation of that as well. Also with impact echo testing, if you've got a rough surface finish, it's more difficult to complete the test. You need to be more careful with your impacts and more careful with the final measurements. So let's talk about what impact echo is. It is a resonant frequency measurement of a structure. We give it the velocity of the speed of sound. We determine the frequency from a impulse, a strike to the surface, and we determine if it's a flat plate, thickness, that's what, and if it's voided, the voiding will change that measurement. So we physically strike the surface and record the waveform. We do a fast Fourier transform to determine the dominant frequency, the resonant frequency of that reinforcing slab, of that concrete slab. And because we know the velocity, we can calculate the thickness. So it's very suited to take a single point measurement of thickness. In this example here, this was on a boat ramp, which got thicker as it got deeper, so between a 500 to 650 millimeters thickness. There are other tools you can use for thickness measurements, ultrasonic pulse echo, but impact echo is quite associated with thickness measurement as a simple tool for thickness. And I was talking about what can you do successfully. So here I've marked in green, here, this region and these regions, that they're an appropriate place to look for a thickness measurement. This is a coated structure that you need a solid coating properly bonded to test through. You can't test on tiles, you can't test on a rubbery coating. You need to be above a minimum thickness, and it'll depend upon which device you have and the way the sensors are recorded from, how thick that is. That'll be a specification for your impact echo system. And you need that flat plate-like element. So internal delaminations will definitely be detected and would affect the ability to measure thickness. I've also marked as poor these edges, because you do have issues towards the edges of a plate, and also regions where the chain's thickness changes. You'll have a sort of zone where it changes from one to the other. So that's, any questions on impact echo or comments on impact echo testing?
Similarly, William, the issues with the reflections from the sides of slabs, you'll find the same thing with the GPR. Also will pick up the sides of slabs, which will interfere with perimeter bars and things like that you're looking for. The other thing is that the impact echo in relation to looking for piers under a waffle slab is probably more appropriate than it is for a GPR.
Can be, certainly. You've got a much...
Go on.
Sorry, certainly you've got a much greater thickness range. I was going to discuss thickness ranges at the end, but that's right. Sorry, you can continue if you'd like to.
No, that's fine.
Thank you very much. I appreciate the input. We have a question. What about curved surface for impact echo, such as the inside of a well structure with a 3-meter diameter? So that's a good question. I particularly called out curved surfaces for like a circular pile or circular column. The echoes inside something like this are very complicated. If you're inside or outside a pipe and you're measuring into that pipe, that's essentially flat in the localized region. It does have a radius, but that radius is of a fixed plate. It's just a curved fixed plate. So you're fine to test say inside or outside a pipe, or inside or outside a well, or on walls with which aren't flat, but you don't want to be testing circular objects from the side. That can be very confusing on the results you receive. Anything more on impact echo, or I'll finish up with pile integrity, and we can maybe wrap up with a few questions and a bit more discussion once I finish recording. I finished the recording today. Okay, continuing. And again, I'm sorry if I cut anyone off. The lag and lack of visuals makes it a little tricky on the webinar. So sonic echo testing or pile integrity testing is very commonly used to look for defects in poured in situ piles. But because we're essentially, with every pile, trying to determine it's been drilled and poured to a compliant depth, you can use sonic echo to confirm depth as well. We do, once again, because we're getting time and we want a distance, we need to know the speed of sound to that material. We also need to be able to get access to the top of the pile, physically bond and place our accelerometer sensor on top. So it needs to be sufficiently flat. Then we'll be able to do our investigation for defects and thickness. The basic principle is you put an accelerometer on, you give it an almighty whack, and you record the time between the strike and the returning signal. If it's very thin, you may find impact echo is more appropriate. Certainly the maximum range for impact echo is 1.5 to 2 meters, depending upon the size of the hammer you use. But column foundations, piles, poles, sonic echo or pile integrity, very commonly used to look for large changes in the structure. So and this is the typical output of sonic echo test, where you have a signal from the hammer blow and the returning signal after the hammer blow comes in at the end. The kind of defects you find, once again, we're not really looking at honeycombing or small voids. We're looking at large changes in the pile geometry. So we're comparing the expected thickness to see if we're shorter than that. If you've got a break some distance down the pile, or a thinning or thickening of that pile, those situations, the crack, the necking, and the bulging, will also return a reflection to the pile test. Typically, if it's a friction pile, so it's not being in physical contact with the solid rock, you would have your sending and receiving blows come in at the same orientation. And if you are going towards a pile which is into bedrock, you'll have a return in the other direction. There's a lot more nuance to this interpretation. You'll get reflections from changes in soil type, changes from soil to bedrock. If you actually have a section of the pile going through the bedrock, you'll get changes from the mentioned defects and other aspects. So again, this is not a guide to interpretation. This is just a quick overview of how sonic echo testing can be used to evaluate measure depths of piles, and calling out that if you're doing that, you need to know the velocity to have a meaningful value. So just a final note about the range of measurement, thickness measurement, which your maximum is, depending upon the dry film thickness gauge you pick. Your ranges are maybe 3.5 or 8 millimeters. Cover meter maximum is around 140 millimeters for 16 mil reinforcing bars. Radar, depending upon choice of radar, maybe 700 millimeters, 800 millimeters, absolute maximum depth for very well performing concrete radar. Utility frequencies, lower frequency energy, somewhat deeper to several meters, depending upon the soil conditions. Impact echo, 1.5, maybe as much as 2 meters thickness with care and slightly different impacts. And sonic echo, so the PAL testing, you're controlled by the ratio, maybe a 21 to 30 to 1 ratio of diameter to depth with those tests. So look, thank you so very much for joining me for the webinar today. I'll stop the recording.